try something a little bit different. Probably going to have to go ahead and invest in a new microphone to use directly into the system. I had to give back the wireless system to the church. It was actually a Shively's wireless system that I was using for the audio on the videos. So if you go to the videos over the next several days until I get this thing worked out better, the audio is kind of poor. I pump it up as much as I can without making it distorted. Try and place in the separate recorder up here and getting 2 tracks, one from the front, one from the webcam, but I'll do the best I can, and I'll try to improve the system by getting some new hardware. Yesterday we started the first of the distinct types of reactions. We're going to learn 3 different types plus several variations of the third. But what was the type of formation we talked about yesterday?
Decomposition.
Decomposition. And a decomposition reaction is characterized by what? How would you say? A decomposition reaction is a reaction where a compound breaks down into its constituent elements, its constituent elemental forms, right? So you're taking a molecule, which is a bunch of different atoms hooked together, and you're taking that and breaking it down into elemental forms. So the molecule produces an element and an element and an element. And as we walk through the process, we started by writing the compound, reaction arrow, elements. So once we break it down by symbols, we go through and check to see if we have any. What's the process? After write down the formula, or the reaction equation, we go through and look at the elements to find out if we have any. It's right there, I know.
Yeah.
Yeah. The homonuclear diatomics, good. So we go through the elements to see if any of them in their elemental form actually exist as molecules rather than individual atoms. We go through and write the subscript 2's on all of those that are homonuclear diatomics. Then we go through and see if the reaction equation is balanced. In most cases, it's not going to be balanced. Okay, so then we have to go through and balance the equation. So that last part of seeing if it's balanced and balancing it is all stuff from last module. The new thing for this module was in a decomposition reaction, we're taking a molecule of a compound and we're breaking it down into its constituent elemental forms. We can't take it any farther, remember, because of Dalton's law. This is what they did to figure out what elements were. They said, hey, we've got this thing that we can break down into smaller things, break it down into smaller things, break it down into smaller things to a point where we can't break it down anymore. Oh, whatever it is we can't break down, that must be an element. Oh, we've got different things that we can't break down anymore. There must be different kinds of elements. And that's how we came up with that whole line of thinking of what an element is. As I promised, today we're going to go in the other direction. And today we're starting with a formation reaction. Page 248 is about where we're at, if you want to track along with us. Notice the picture that they have here on figure 7.2. It's a hydrogen balloon. They show the hydrogen balloon there in a classroom. Hydrogen's, it's lighter than air, so it's floating. Then they bring a match close to the hydrogen balloon. When the heat from the flame pops the balloon, because that's the reaction that happens first, right? The balloon pops. Don't worry, popping balloon doesn't cause that explosive look, that fireball. That fireball comes when the hydrogen that's inside the balloon and the oxygen that's in the air around us combine. And when you take hydrogen and oxygen, it produces water, H2O. I could have just written H plus O produces H2O, but then I would have to do, in much the same way when we did the decomposition reaction, now I have to look over at my reactants and ask the question, are any of these homonuclear diatomics? And the answer is yes, hydrogen and oxygen are both homonuclear diatomics. So hydrogen reacts with oxygen to produce water. Now, if you take that flame, you put it near the hydrogen balloon, it pops and there's a fireball. Yes, there's energy being released in this type of reaction. But water is formed, and it's formed in that phase as a gas. So we have water vapor that's formed. It doesn't suddenly precipitate water out on the floor, make a wet spot, right? This reaction, this fireball that happens real quickly, is energy released from the reaction of hydrogen and oxygen. It doesn't cause it, it's released from it to produce a molecule of water. So in this formation reaction here for water, we need to go back through, and now we need to balance it, right? You can see they do that on the page, but real quickly, if I do hydrogen and oxygen, reactants products, I've got 2 hydrogen and 2 oxygen. On this side, I have 2 hydrogen and only 1 oxygen. How do I get 1 oxygen? If I go with fractionals, I can ask the question, how do I get 1 oxygen on this side? If I do multiples, I ask the question, how do I get 2 oxygens on that side? See, it's the same question. One of them using fractions and one of them using whole numbers. The way that I typically do it is see where I'm lacking and build it up. So my technique would say, okay, 2 oxygens and 1 oxygen. I'm lacking oxygens on this side. So I need to increase the number of oxygens to 2. I do that by putting a 2 in front of the H2O. That gives me 2 oxygens, but it also now gives me 4 hydrogens. I need to fix the hydrogens. I'm lacking hydrogens on the reactant side. I have 2, I need 4, and I do that with 2 sets of 2. 2, 1, 2, 2, the greatest common factor is 1. That's my balanced reaction equation. Real quickly, if we did it the other way, using the fractionals, rather than asking the question, what do I lack and what do I need more of, if I ask the question, what do I need less of, and use fractions, again, hydrogen, oxygen, hydrogen, oxygen, excuse me. What do I need less of?
Oxygen.
I need less oxygen on the reactant side, right? How do I get 1 oxygen? Take a half of the oxygen, correct. That would give me 1, and now it's balanced. But I have to look at this and ask myself, are there fractional coefficients? Yes. So I need to get rid of them. How do I get rid of the fractional coefficients? Well, the only fractional coefficient is this 1/2. So I'm going to multiply everything by my denominator of 2. So this implied 1 becomes 2, this half becomes 1, and this implied 1 becomes 2. And there I have the balanced reaction equation again. Looking at it, 2, 1, 2, greatest common factor is 1. I'm done. Okay. Example 7.2 on 249 asks to write the chemical equation for the formation of magnesium with CO3. What is the polyatomic ion CO3?
CO or
CO.
carbonate. Carbon.
Well, it has
I
a
think it's carbon. Yes.
okay. Magnesium carbonate, and it has a charge of 2 negative, right? Because magnesium, you can check that by going over here and saying magnesium is a column 2. It wants to become positive 2. If it's positive 2, it needs to be balanced by a negative 2, and so that's my charge. So let's write the formation reaction for this. I put it a little bit too far to the left, but I'll go ahead and work with it. The reaction equation. In other words, that's what I need to produce, or the formation reaction. I need to produce. So it says, write the chemical equation for the formation of, that's what I need to end with, the formation of magnesium carbonate. So looking at my elements from left to right, magnesium, carbon, and oxygen. Immediately ask yourself the question. Are there any complementary diatomics? Are there? Oxygen, okay. Ask yourself the next question. Is it balanced? No, it's not balanced. So, balance it. How do you want to attack it, Seth? Reactant oxygen? What are you going to do to it? I'm sorry?
No, you have to do this.
Okay. What do you want to do to it?
Put 2 in front of everything.
2 in front of magnesium carbonate. Okay. 2. So make it 2 and 2 and 6.
Put 2 in front of magnesium on the other side.
2 mag.
And carbon. And then put an oxygen.
Okay. Any questions on that? What if we did it the other way? That's the question. Not where am I lacking, but where do I have too much? Okay, so I'm going to get 2 when I have 3. 2/3, right. I have 2, I need, excuse me, I have 3, I need 2, so it's 2/3 of that. Okay. I need 2, but I have 3. That's how you come up with your fraction. I need 2, but I have 3. I need 2, but I've already got 3 in there. See that in the oxygens? So I need 2/3 of that. When I do that, my magnesium now becomes 2/3. My carbon becomes 2/3. My oxygen becomes 2. This is not the way I would go, by the way. I see that right away. I'm going this technique over here. But if we walk it through, it says if we do the math right, we should end up with the same result, right? We should end up with the same result. So I have 1 magnesium, I need 2/3. Multiply by 2/3. That'll give me 2/3. Carbon, I have 1, I need 2/3. That gives me 2/3. Now we're balanced. Fractionally, all my denominators are 3s, right? So I'm going to multiply everything by 3. If I multiply everything by 3, the 3's cancel, leaves me with 2, 2, 3, and 2. 2, 2, 3, 2. So again, I'm just doing them both, not that you would always do both, but hopefully you get it. And over a while, you'll pick up which technique will get you to the right answer quicker. Or maybe not quicker, but more in tune with your math ability. Like what's obvious to you, and choose the one that works best for you. Any questions then on formation reactions? This is basically the inverse of a decomposition. Rather than taking a compound and breaking it down into its elemental forms, we start with the elemental forms and we produce the compound. And in the same way we mentioned about the formation, or excuse me, the decomposition reactions, a decomposition reaction that takes a molecule and forms a molecule in elements, if it breaks it down, doesn't add anything to it or take away from it, but just breaks it down, it is technically a decomposition reaction, but for this course, we're going to take it all the way to the elemental form. The same way with the formation reaction. You can take a molecule and an element and combine them to form a greater molecule. But for this class, what we're going to be doing is taking a molecule and breaking it down into all of its elemental forms. We're going to take all the building blocks apart. Okay? There are intermediate steps where you take something, you decompose it part way, then you decompose it part way, you decompose it part way, and eventually get it to all elemental form. We're basically going to say we're going to take it all the way to the extreme. On your own 7-3. You can put this in your notes if you'd like. Even if you're not like, it's probably a good idea. On your own 7.3, write a balanced chemical equation for the formation of potassium chloride. Okay. So the first part of your knowledge base for an exam or anything would be write the balanced equation for the decomposition of. If you hear the phrase decomposition of, that means it's going to be the molecule produces, right? The decomposition of, or maybe use the abbreviation they used before of ABC. The decomposition is ABC becomes A plus B plus C. That's the decomposition. I'm decomposing, taking the pieces apart. The decomposition reaction. So write a balanced decomposition reaction for the molecule ABC. If the question is write the balanced reaction equation for the formation of molecule ABC, then I start with for the formation of ABC, and it must be A plus B plus C. So the first one, the decomposition of ABC. The second one, the formation of ABC. So the on your own says, write a balanced chemical equation for the formation of, this form, for the formation of potassium chloride, for the formation of potassium chloride. Go ahead and start on that. We'll just take a few moments to get you ahead of me, and then we'll walk through it. What's the charge of the chlorate ion? -1, because potassium is a column 1 metal. It's +1, so it must have a -1 charge. Okay, since we're doing the formation reaction of, we put the molecule we're trying to form at the head side of the arrow. We're forming that. So we must have the elements potassium, chlorine, and oxygen. So Tyler, next thing I ask myself is, do I have I ask myself the question. After I write down all the elements, I ask myself the first question. What is that question? What do I ask myself?
I don't understand, but it's the little things.
The little things. Okay, the subscripts, right? Ray's getting this one down now. Go ahead, Ray.
The homonuclear diatoms.
Look to see if I had any homonuclear diatomics. Do I have any?
Yes.
Yes. 2 of them, right? Chlorine and oxygen. Little thingies. Yeah. So I wrote little thingies. In this case, the thingies are 2. Over here, the thingies are 3. So the subscripts, 2 and 3. So chlorine and oxygen. Oxygen is not column 7. Remember, the homonuclear diatomics are column 7. Nitrogen, oxygen, and hydrogen. Okay, so check your format. That's why we had to learn them before, because we knew eventually. See, whatever module that was, like 1, 2, 3, somewhere back there. Can't just dump that stuff. Everything we learned comes back to play somehow. That's why you can't finish a module done with that. Everything is building. Potassium, chlorine, and oxygen. Chlorine and oxygen are homonuclear diatomics. Next question. So Anna, I ask myself, okay, I've got my homonuclear diatomics. Next question is it balanced? Good. No, immediately it's not, right? Because I look for the subscripts, I got a 2 and a 3, I know it's not balanced. which means now I go back into the last module's work and balance it. So potassium, chlorine, oxygen, reactants, products. I have 1, 2, 2. And on this side, I have 1, 1, 3. So Emily, how would you like to attack this? What are we going to fix first?
On the product side, multiply by 2.
So we're going to bring chlorine up to 2 by multiplying this whole molecule by 2. Okay? If we do that, it's going to change everything. So I just erased it all. It's going to bring us to 2 potassiums, 2 chlorines, and 6 oxygens. Okay? So Haley, where do you want to go now?
I'll put a 3 is then 1.
3 in front of what?
4.
Over here, chlorine. We've already balanced the chlorine, right? Chlorine is balanced. We need potassium or oxygen to be balanced. That's what we're going to look to first. And what is one of the hints I told you before?
Yeah.
Leave the elemental forms till the end. Because I look at oxygen here, and I could just throw 3 in front of that and balance the 6, but I still have potassium left out there, right? But it's all on the reactant side, and these are all elemental forms, right? Potassium. So in a formation reaction, if all of your cleanup is on the reactant side, it's a piece of cake. On the decomposition, if all of your cleanup is on the product side, it's a piece of cake because it's all the elemental forms. Whenever you put a number in front of a molecule, that's when you mess up multiple things with one move. So rather than changing the chlorine, which is balanced right now, we need to balance the potassium, and we'll do that by increasing from 1 to 2. And how do we do that?
You put a 2.
Put a 2 in front of the potassium. Good. So that 2 potassium now changes this to a 2. And the only thing now that needs balance is the oxygen. We're going from 2 to 6. We need 3 sets of 2 to give us 6. And we balanced the formation reaction of potassium chloride. So I would encourage you tonight, this is all we have for reaction formations. The biggest thing is which way does the arrow go and which way does the molecule sit on. It's either over on the left side, which means it's being decomposed, on the right side, which means it's being formed. Write the molecule. On the other side of the reaction arrow, write the elemental forms, check for homonuclear diatomics, and mark them such. See if it's balanced, and if not, balance it. For those of you that want to do your homework as we go through, this will answer review questions 3, practice problem 2, and extra practice problem 2. It is all on formation. So if you were to do that homework tonight, you'd be doing it close to when it was taught. Okay? We'll keep you on track. So again, that's review question 3, practice problem 2, and extra practice problem number 2. All right. Now we move on to some of the most explosive reactions, as well as some of the most benign reactions we're going to talk about. Both are combustion reactions. So third section is combustion reactions. And as I mentioned before, when we think of combustion reactions, we often think about things burning. The pyros in here, they're all like, yeah, let's do combustion reactions. We'll go into the parking lot and we'll build a bonfire and we'll throw different chemicals in and watch it go right and burn up. Okay? That is a combustion reaction. Combustion, remember, we tend to think, just like we tend to think air is nothing, which we know it's not now, but we tend to think that combustion means burning. Well, what is burning? As I said before, we actually talked about an explosion as a reaction formula, or an explosion as a reaction that forms water. And it was a formation reaction, not a combustion reaction, or at least described in that way. For combustion reactions, the primary definition is that a combustion reaction is when something reacts with oxygen. when something reacts with oxygen. There's two different primary ways that happens. One is by what we think about. We think about burning. Something's going to combine with oxygen, and with the whole fire triangle, we've got a fuel, we have oxygen, we've got energy. Okay? And if you bring the oxygen and the fuel together, and we're not going to get to this to probably chapter 15 if we get there, but if there's enough energy inherent in the two products, if there's enough energy for that reaction to kick off on its own to become spontaneous, it'll happen. Now, certain things, you bring them together, boom, they explode, they burn, just because you brought them together. Boom. Sometimes you bring things together and the system needs more energy for it to react. And so you bring them together, but then you've got to heat them. You've got to introduce energy into the system. I mean, that's why, for example, a stick of dynamite is relatively stable, and you need to light it so that the heat makes its way up the fuse into the container. That heat starts the reaction. The reaction of those products in that small space suddenly takes up more space than is available, and boom, it explodes. Nitroglycerin, on the other hand, you don't have to do anything to nitroglycerin other than shake it up a little bit, right? A little bit of motion. You don't really need to add any heat to it per se, but you're going to mix it up, and it's the kinetic theory of matter. Remember, as those molecules start moving around, they start interacting with each other, they start a reaction that, boom, blows up. So, when we think about combustion, I want you to remember that combustion is basically things reacting with oxygen, and that reaction can look very different. On page 250, I actually start talking about combustion and the combustion of metals. Combustion of metals. So 2 magnesium, here they give you the reaction equation of 2 magnesium, it's in its solid form, plus oxygen in the gaseous form, reacts to produce 2 MgO, magnesium oxide. Now, maybe you haven't thought about metals as burning before. Okay? Haven't thought about metals burning. It was an active concern of mine in a previous life when I was a helicopter pilot in the Marine Corps. I've seen magnesium gearboxes catch on fire. As a matter of fact, one of my dubious distinctions is I have the most on-scene commander time of any other helicopter pilot during Desert Storm. What does that mean? That means it was very, very lucky for you to fly with me and very, very unlucky for you to be my wingman, because my wingman went down. In one case, on the CH-53 Echo, there are 3 engines that feed into one main transmission that turns the main rotor head. That transmission is primarily made out of magnesium and zinc and a few other things, and there are many metals that burn. Matter of fact, they burn very hot, very bright. We were flying out of Jubail, Saudi Arabia, and going out to do night vision work, using night vision goggles to go out and do some missions, and saw a spark and brilliant white light coming out of my wingman behind the rotor head, and figured out that he had a transmission fire. The deal is, once those things start on fire, you're not going to stop it. I've had 2 instances where I've had burning metals occur. Once was back in 1984, I'm going to guess 84, when I was on a Knox class frigate. We had a magnesium fire on deck. The burning metal hit the deck and started to melt through, and we went under the deck with a big can of sand, and once it was bubbling through, caught it in the sand, took it out, and dropped it in the ocean. Okay. On the magnesium fire in the helicopter, it's a slow, hot burn. And so they landed the helicopter, I circled overhead to keep them safe. They went through and they stripped out all the machine guns, all the crypto gear, they stripped everything out of the helicopter. They had plenty of time to clean it out of anything significant, but they were not going to save the helicopter. We had it cleaned out, we picked them up, we picked up all the gear, we came back to it later, it was just a gooey mess. Metal fires tend to be extremely hot, extremely difficult to put out, because it's not combustion in the way you typically think of it. It's not like a pile of leaves in your yard that's on fire and you just want to go spray water on it. It doesn't work. Okay? Because what's in water? Think about it. If you decompose water, what do you get? Hydrogen and oxygen, right? What are those? Aren't they flammable? Don't they feed a fire? At a certain point, the water doesn't smother the flame; it feeds the flame. Okay. So don't always. That's why there's different kinds of fire extinguishers, ABC fire extinguishers, and so on. There's different ways to treat different fires. Typically, for metal fire, get out of the way and get it out of the way. The reason why we went and caught it is because in the ship is if we didn't get it overboard, it would keep burning through. And as we dumped it over, you know what? We looked into the bucket. You know what we saw? Very glassy looking liquid. Because what is glass? Sand. Glass is a molten form of sand. So it was kind of a weird experience to see this bucket go over with a burning metal in it, which was sand, and it wasn't really glass, but it was somewhere between sand and glass. It was this weird stuff. So, combustion and combustion of metals. This is the reaction for the combustion of magnesium. Magnesium, in the presence of oxygen, it forms magnesium oxide. Okay. A metal and a nonmetal, which means it's an ionic compound. Magnesium and the I form of the nonmetal, magnesium oxide is the name. That's one form. The second form they have down here is 4, and what is Fe? Iron, right? It's not, from the Latin ferrous, it's not I. I is iodine. So when you see iron, make sure you go to Fe. It's one of the ones we had to memorize. 4 ferrous, 4 iron, plus 3 oxygen, reacts to produce 2 Fe2O3. Notice here that we've got iron reacting with oxygen to form a compound. It is, in a sense, a formation reaction, isn't it? I mean, aren't I forming this molecule over here? I'm forming this molecule, right, from magnesium and oxygen. I'm forming ferrous oxide from iron and oxygen. It is a formation reaction, but it is also a very specific kind of formation reaction, the kind that uses oxygen as one of the reactants. Now, as this reaction here is a very dramatic, white, bright light, lots of heat. Do you know what this one is? I mean, does anybody here know what ferrous oxide is? You see it all the time. Rusted metal. This is rusting. So, burning the metal, white, hot, intense, and rusting of iron, an iron bar you leave out, a lawnmower that's supposed to come in the fall but ends up being there in the spring when you go outside and doesn't quite look the same. It's all brown and kind of, all this weird acne on it stuff. What's that coming from? Iron oxide. It rusted. They're both forms of combustion. We don't tend to think of rusting as combusting, but rusting is a form of combustion reaction. Why? It's an element or compound that's reacting with oxygen to form a new compound. You have a bar of iron that gets iron oxide on it. The iron oxide is not just simply discolored iron. It's a different compound. It's something other that's been created from the iron in the object, and the oxygen could be from the air, but what tends to make it happen much more quickly is oxygen associated with water. The water being on the iron causes it to begin to rust. Okay. So we're not going to go into a lot of how do we do this, and let's do balancing equations and all of that. Just as you look at a reaction, you can say that this is hopefully you can see that both of these represent formation reactions, and that in both cases, one of the elements, one of the reactants of the equations is oxygen. So something combines with oxygen to form a molecule. That's a type of formation reaction known as combustion. In this case, they're both the combustion of metals, because metals are combining with oxygen to form the molecule.
So for combustion, it has to be a metal that comes out.
No, it does not have to be a metal. But just because we tend not to think of metals, they use these two examples of it. It could be a carbon-hydrogen chain, or a carbon-hydrogen-oxygen chain. Methane, ethanol, those are all fuels, right? In your car engine, some run, right? Going down Dixie. So you've got a fuel that combines with oxygen in the presence of heat, the spark, and pressure in the piston that causes a reaction that converts them into something that takes a greater volume. That greater volume forces the piston out, which drives the cam, which drives the tram, which drives the wheels. Okay? So it's not just metals. This is a type of combustion reaction known as a combustion of a metal, but it doesn't have to be a metal. So that's actually 3 points of teaching here. These are formation reactions, they're combustion reactions because they react with oxygen, and they're combustion reactions of metals because in this case both of these are metals. But they don't have to be metals to be combustion. Matter of fact, they're typically not in most cases. The example 7.3 on the right hand side that we're about to do is a butane pocket lighter works by evaporating and then burning the liquid butane. Write the chemical equation for the combustion reaction. So there it's a C4H10 molecule. A carbon, hydrogen reacts with oxygen. Okay. Now to that point, there are two types of combustion reactions, complete and incomplete combustion reactions. This one here talking about complete combustion, and we'll just go ahead and do the butane example. Again, we write it up on the board. Example 7.3 on 251. It says a butane pocket lighter works by evaporating butane. Okay, write the balanced equation for the complete combustion reaction. Okay. So in these complete combustion reactions, what are going to be produced is carbon dioxide gas and water vapor. If I tell you that I've got a fuel and oxygen that produces, or that combusts, your assumption is going to be if something has combusted, again, it doesn't fit for metals. These metal examples we have here. But if a non-metal combusts, what's going to generally be formed is carbon dioxide and water. Carbon dioxide and water. So if I say a combustion reaction of something, and I don't tell you anything else, in this case, butane, C4H10. Write the balanced combustion reaction for butane. That might be the whole question. The balanced reaction for the combustion of butane. What is it? Well, if it's a combustion reaction, I know that one of the reactants has to be oxygen. So I know that it has to be oxygen. I know oxygen is a homonuclear diatomic, so I'm just going to get used to writing plus O2. That tells me I'm combusting butane. And the standard products of combustion are going to be CO2 and H2O. How do I know that? I assume that because it's combustion, and it's combustion of a nonmetal. Okay? So combustion of a nonmetal, you can start by assuming it's going to produce carbon dioxide and water vapor. And since it's combustion, it requires oxygen. So the only thing I need to give you is what is burned, what's being burned, what's being combusted. In this case, write the balanced reaction equation for the combustion of butane. Butane plus oxygen produces carbon dioxide and water. So again, if I give you the ethanol, propane, CH4, methane, whatever, and I say write the balanced combustion equation, or write the balanced reaction equation for the combustion of methane, you say methane plus oxygen produces carbon dioxide and water. Cool. Just write it down and then start balancing it from there. There's nothing, and I'm going to save us some time here, there's nothing unique about this balancing than anything we've already done. It's the same basic format. Write down all the elements, reactant side, product side, and go through the technique of balancing it. The key here is for a complete combustion. And if you're not told complete or incomplete, generally we're going to assume it's complete. It's a complete combustion. A complete combustion of whatever fuel You write the equation by the fuel plus O2 produces CO2 and H2O. Boom. It's not going to tell you that it forms CO2 and H2O. It's not going to tell you to add oxygen. That's part of knowing what a combustion reaction is. Now, from that, there are some nuances to complete combustion and incomplete combustion. And as I just said, typically all the combustion reactions that we tend to have are complete combustion. Complete combustion is, here's the difference. And this is not going to be balanced, but I'm just going to use this as an example of what you should write down before you do the balancing. I'm going to hold out right here for just a minute and say, write a balanced reaction equation for the combustion of butane. Butane plus O2 produces CO2 and H2O. If I said, write the balanced reaction equation for the incomplete combustion of butane, you would write down butane plus O2 produces carbon monoxide and H2O. See, the difference here is incomplete combustion doesn't give me, if you want to think of it this way, the preferred outcome. The preferred natural outcome is for butane and oxygen to produce carbon dioxide and water, because carbon dioxide and water is the typical product of combustion. However, there are going to be times when it's not possible to form carbon dioxide and we end up with carbon monoxide. When might that be? Well, what's happening? Real simply, what's happening here? Incomplete combustion. If the preferred would be CO2, but we're only getting CO, why? And again, the simple answer is, there's just not enough oxygen. We're running out of oxygen. There's not enough free oxygen for the carbons to match up with two oxygens, and so they're settling for one. Okay? You've been choosing dodgeball players for so long, there's just not that many options left. You say, okay, and you're dealing with what you have. Do the best you can with what you've got. And carbon monoxide is a legitimate molecule. It's not the preferred molecule, but it is a legitimate molecule. And so when the reaction is unable to form CO2 because of a lack of oxygen, it'll begin to form CO, carbon monoxide. Now, what is the difference physically for you and me between carbon dioxide and carbon monoxide? Pardon? For you, what would be your concerns? What's the significance for human beings between carbon dioxide and carbon monoxide? Carbon monoxide will kill you. Carbon dioxide could kill you if that's all you had. It's kind of like water is good for you, but you'll drown in it. Carbon dioxide is generally okay for you, but if it's all you've got without enough oxygen, it'll kill you. But breathing carbon monoxide in your system is a poison, and it will kill you. And so a note of application here. Some people ignore the little warning labels on those heaters that say, not for indoor use. Okay? Why would a heater that's designed for outdoor use not be able to be used indoor? And basically the idea is the system's not efficient enough to pull oxygen in for combustion. And so outside, if you're producing carbon monoxide, it's getting diluted into the air and it's not a problem. But you bring that into a home and you put that in a small space and you have incomplete combustion, and that gas that's being released after the combustion into the space isn't carbon dioxide, it's carbon monoxide, eventually the people in the room die. Or maybe you've got one of those ventless fireplaces, right? Where they've got a fireplace in the corner, and it used to be that everything had to be vented outside, but they came up with very efficient burning mechanisms so that rather than producing carbon monoxide, they produce carbon dioxide. And they allow you to release the carbon dioxide into the room. That's fine. You do need some fresh air coming in every now and then to replenish the oxygen, but carbon dioxide is not going to kill you. But if the burner in there becomes inefficient, and it can no longer produce the appropriate amount of mixture between in the combustion to form carbon dioxide, starts forming carbon monoxide, or if the space is so tight that as this combustion is taking place, it's burning up the oxygen in the room. It's slow. Everybody's starting to get a little bit lightheaded because the oxygen's all getting burned up. Pretty soon, you go from being lightheaded to being dead because the burner stops making carbon dioxide, it makes carbon monoxide, and it kills you. Or the catalytic converter in your car. One of the byproducts of the combustion in your engine is a lot of carbon dioxide, but also carbon monoxide. And maybe you know those old-fashioned shows where people used to want to commit suicide, and so they would drive the car into the garage, put down the door, and just sit in it. That's how people used to kill themselves, was using automobiles. They go to their garage, they sit in their car, they start the engine, and they would fall asleep in their garage because the car would be putting out carbon monoxide. Eventually, the level would rise to the levels that are poisonous and kill them. And that process, they would get a pretty decent headache, but they would eventually pass out, and then they would die in their garages. And so it used to be a fear that you would hear, a car running in a garage, and if the door's not up, it's a danger signal. People could get hurt. If you go out to warm up your car, you would always put the door up to warm up the car because you wouldn't want to have all that poisonous gas be in that small space. Well, more modern cars have catalytic converters on them. And the catalytic converter uses a process where carbon monoxide goes through the catalytic converter, and because of an exchange that takes place in the catalytic converter, it converts carbon monoxide into carbon dioxide. Now, carbon dioxide is a greenhouse gas, right? So there is a concern there. But there's a much more immediate concern if your car is putting out carbon monoxide. And cars with catalytic converters, people that take them into their garages and close the door and decide they're going to sit behind the wheel and commit suicide, generally just end up with a really bad headache. They're not able to produce the same level of toxins as there was before the catalytic converter. So here's the main point, takeaway from this. A combustion reaction is something reacting with oxygen. In the case of a nonmetal here, we've got that something, combustion is that molecule combining with oxygen, and the natural products are carbon dioxide and water. And again, you're not going to be told the products are carbon dioxide and water. You're expected to know that the products of combustion are carbon dioxide and water. However, if you're told that there's an incomplete combustion, the product of reaction is not carbon dioxide and water, but carbon monoxide and water. And the danger being, this is poisonous to humans. This one is dangerous in high concentrations. There's a big difference. Okay? So those of you that are tracking homework, we have just covered review question 4, practice problem 3, and extra practice problems 1 and 3. Can I say that for you? This section on combustion reactions is review question 4, practice problem 3, extra practice problems 1 and 3. And I just noticed too, we did incomplete combustions. Go ahead and add to that review questions 2, 5, and 6. So 1, 2, 3, 4, 5, 6, 7. We've covered 10 review questions, practice problems, and extra practice problems today, the content that those problems are based on. I would encourage you to go ahead and try to do those. Keep building your homework in advance rather than waiting until the day before it's due. All right? Any questions for me before the bell? Just let me go.